Happy Thursday, and greetings from wherever I am. I want to talk about acids and bases today, and I don't want to spend your whole day listening to me talk on a video. I mean, this is hard stuff to do. Following someone listening on a video, I get it. So speed me up when you need to, slow me down when you need to, but let's get through where we're going. And where we're going is we don't actually know what an acid and a base are. I mean, sure, we know an acid at some point dissolves things, but so does a base. We know that an acid can cause really nasty chemical burns, but so can a base. We know that acids and bases deserve respect, but so do a lot of chemicals in my lab beyond them. We know they have something to do with chemical reactions, but then all chemicals do. Really, it occurs to me that most high school students, including you watching this video, probably don't actually really know what an acid or a base are. And you might notice on the sheet that your sub was supposed to give you your notes that you're following along, and I'm going to actually check and make sure that you followed along with me on the video. Ask, what's an acid and what's a base? And it's a question that's actually more difficult to answer than it seems. Well, an acid's an acid, a base is a base. Well, that's great, but why? And answering that's going to take us a whole day between notes and this video. So let's start off with where we are. We've seen reactions, and we know that we can identify the oxidation state. So here's an acid-base reaction between sodium hydroxide and hydrochloric acid. That'd be great. Let's just go ahead and figure out where things are being oxidized and reduced. Look, sodium went to +1. Oh, that must be a spectator. Oxygen went to -2. Ooh, that's a spectator too. Oh my gosh, everything's spectators, right? I've got a problem. And my problem is I don't know how this chemical reaction happened, because the framework we spent a long time developing about moving electrons around just failed, right? If you look at the equation I put at the top of this, everything we say says nothing happens here, and yet I've written an equation that clearly says two chemicals turn into two different chemicals. So how in the world did that happen if it didn't happen the way we understand reactions happening, by moving electrons? That's actually a pretty good question. And answering it is really what we're going to be doing from now until spring break. Answering it isn't so easy as just saying, well, a proton moved, although that's partly what happened most of the time. It's more complicated than that. And so let's start off by describing acids and bases, because we really don't have a great framework for what acids and bases are. So on your sheet, you'll notice I've given you a whole page here to talk about the properties of acids and the properties of bases. And I'm not going to spend a really long time on this because, well, we know what they are, right? We know more or less what they are. So we know acids because we've eaten acids before. We know what an acid tastes like. Now, going around my lab and tasting acids isn't awful. I can't underline how terrible an idea that is. But if you did, they would just taste like really concentrated forms of like Warheads candy. Now, Warheads or Sour Patch Kids or any of these sour candies, whatever they all pretty much are based around two chemicals, malic and citric acid. I circled them over here in the nutrition facts. And these chemicals have that very sour, it's not a bitter taste, it's almost that puckering taste. And almost an electrical taste to me, but it's not pleasant, but it's also not unpleasant. Acids generally have more or less that taste. You know what they are: lemons, vinegar. There's a lot of things that are, well, acids in foods that we like. But again, tasting them isn't the best way of doing things. So yeah, we have a property of acid, but it's kind of worthless to us. I mean, I can't taste my acid in lab. And in general, I shouldn't go around just licking chemicals. That's a bad idea on a good day, let alone, again, when we're talking about things like this. So we got to come up with some other properties. Acids burn your skin. Well, that's also a property that I don't really want to test. And I do want to point out that like the acid burns thing is generally overstated. Now, if you do get acid on your skin and you don't wash it off, like we're talking strong acids, like the battery acid here or the stuff we work in the lab, it's going to itch, and then it's going to kind of sting like bees. Also, it's going to really hurt as you're getting a burn, because it's taking the water out of your skin and burning it. I mean, you are getting a chemical burn. But it doesn't happen like immediately. It's not like just bam, acid burn. For the most part, there are acids that do act that way, especially when they're warm or even hot. But for the most part, the fact that an acid burns the skin is just kind of an interesting note that we are saying, well, I don't want to mess with acids. It's not really a great way of testing, is this an acid? I mean, there are other things, after all, that if I put on my skin, they're going to burn them. I am certain that if I were to put liquid bromine on my hands, which well, isn't an acid in a formal way, that would also burn it. Or if I picked up sodium metal, that would also burn them. So this isn't a great test, but it's something to be aware of when we're talking about acids. They conduct electricity just like most ionic solutions. So if you put acids in and you run electricity through them, you can make a wire out of the acid, which is great. So here you see hydrochloric acid, and here you see acetic acid, which is vinegar. And both of them, even though there's no way for the wires to connect down here, right, they're still making the lights turn on. This is a little more useful because I can at least measure something about the acid using the conductivity of it. You can see, of course, that for the same thing, the HCl seems to be brighter for some reason. We can talk about why that is later. But now we're getting somewhere. Okay, yeah, tasting the acid, feeling the acid, those aren't great. But the fact it's a conductor, that seems more useful to me. And in a lab, I can check for an acid using a special thing called Litmus paper, which is literally just a piece of blue paper that when you put it in acid turns red. Okay, this sounds a lot better than licking my acids or touching my acids. And it's generally the way that you were taught to check for acids, or at least that's my guess. Most grade school teachers will introduce acid using litmus paper. And so knowing that it turns blue litmus red is helpful. And frankly, even when I'm in a lab, sometimes I use this technique. It's, well, true for acids. But all these things aren't really talking about acids, they're talking about effects of acids. Really, an acid is this. It's something where you have more hydronium. What the heck is hydronium? Than hydroxide. So in this box here, that's what I'm asking you to write down. That an acid is defined by excess amounts of H3O+. Okay, H3O+ is just a chemical. I will deal with what it is later on in this video. For now, though, we need to know that an acid is defined by H3O+, not OH-. And so over on the left here, I've got lots of acids that you probably have some in your house. Different kinds of vinegars, different kinds of medicines, soda, wine, whatever. Things that are acidic. They're not like crazy acidic, like they're not like the acids we work with in lab, but they're also nothing to turn your nose up with, especially like the soda or the vinegar are actually quite strong acids, at least in terms of their concentration. In other words, they have a lot of H3O in them. Okay, so again, going through the properties of acids, they taste bitter, they burn your skin, they conduct electricity, they turn litmus paper red, and they contain lots of H3O. Bases are pretty much going to be the opposite of that, right? Bases don't taste sour, they taste bitter. If you've ever eaten baking soda or baking powder, you know exactly the taste I'm talking about. It isn't pleasant. In the way that acids have that pleasantness, you can make candy out of them. Not a lot of people would make a basic candy. It does not taste good. You kind of just want to spit it out as soon as you taste it. Now I said most people because there are some people in the world who do coat candy in bitter stuff like sodium carbonate. And okay, most people don't care for this flavor, but it is an acquired taste in a cultural food in parts of the world. I'm just going to tell you, for the most part, you don't like how this tastes. So a bitter taste indicates a base. And again, a taste test isn't a great way of going through my class. It's not a great way of measuring things. So we got to come up with something else. And again, we could touch them, and it's going to make my hands feel slippery, just like I've rubbed soap on them, because of course I'm turning my skin to soap. We've talked about this a lot. And again, touching acids or touching bases, touching or eating acids or bases, it doesn't make sense to do that. We can't do that. But I should know that if I'm getting a burn and it's because my hands are slippery, it's probably a base. And that actually does matter a little bit, because if I don't know what I'm working with and I feel that slipperiness, I know that I have to go wash my hands now, otherwise I run the risk of a burn like this. And these are very nasty burns. I've gotten one, nothing like that, before on my arm from a stray splatter, and they do hurt quite a bit more than they probably seem like they should. It's quite a bit like a strong thermal burn from touching something really hot. It would be nice if they didn't conduct electricity. It'd be really easy to test, but that's not true. Bases, in fact, do conduct electricity just the same way. So right now, we have three things that aren't very useful. They're bitter, they feel slippery, they don't really do anything besides conduct electricity, and so I'm kind of stuck. Right? Again, just like in acids, most of the properties of bases don't help me identify them. They do turn the opposite true. They turn blue. So if you've got pink paper, it turns it blue, just like acids turn blue paper pink. They're just reversible processes. So that's nice. But it's not enough. I mean, okay, this is useful. Like again, tastes bitter, feels slippery, conducts electricity, and here, red litmus paper, blue. But the other thing, and there's a reason why I drew a box here, seems to be I need to talk about the concentration, the molarity of some ion to actually understand what a base is. And to do that, well, I should just say the opposite is true of an acid. If an acid is defined by H3O, then a base, down here in the bottom box, is defined by OH minus. Apologies. So if I've got more OH minus than I've got H3O plus, well, I've got a base. And that definition is a lot easier to use because I can measure OH minus or H3O plus. Just like the acid, this is really the definition I'm going to use here in chemistry. And you've got bases at home, and you might have noticed when we're talking about the acids, they were all food. And when we look at the bases, they're really not food. I mean, okay, tonic water, yes. But like drain cleaner, bathroom cleaner, stuff like that, stuff you certainly unequivocally do not want to eat. So there is a difference. The things you encounter in your life that are bases tend to be less foody than the acids. I know, I think that's kind of interesting, actually. So we're there. We know a little bit about what like acids and bases are. Let's take a 15-second breather here. So I thought for just a few seconds, it might be interesting to talk about what I'm actually doing right now. So if you didn't know, Rockhurst competes in something called FIRST, where we build these big robots. This isn't our competition right now. We are going to play here in a day or two. But these are the same game we're playing. So this year's game involves big plastic panels called hatch panels and round kickballs. And the game pretty much revolves around putting those through certain slots. The robots playing here are quite good. These are the first week finals. And by the end of the week, or 6 weeks that these things happen, we'll end up seeing quite a bit better play than this. And it comes down to designing and building robots that can do these tasks. Now right now, these aren't really robots. These are more remote control cars. They're being driven over thinking for themselves. But there are times when the robots are thinking for themselves, and within each task, there's probably some autonomous stuff going on. So, for instance, right, there's a lot of defense being played, but as this red robot lines up for the ball, it will probably be using a camera to figure out where the ball is and pick it up. Those kinds of things are not just the driver moving around. And so it's kind of cool to see these things happening and see them being played out. And it's really neat to think that high schoolers are doing this. So, we'll see how we do, but, Rockhurst Robot would be probably on par with what you're seeing here in this match. All right, so welcome back. We need to talk about water for a moment. It should be pretty clear this acid-based stuff is going to come down to H3O plus and OH minus, right? That there's no way around that. And there's no way around the fact this is going to do something with water. We've been talking about water for the past few days in terms of molarity and stuff like that. And water is a strange chemical. I mean, think about it. When you freeze it, it gets bigger, for instance. That's not used to your life. And one of the things that's weird about water is it can react with itself. So the back page of the notes I gave you, right, the front you just filled out, I want you to write down this formula. That water plus water, what the heck, Nendick? Okay, water plus water, trust me, makes H3O and OH minus. Now, there's some weirdness going on, like, what's this double arrow? Why is this an acid and this a base? Don't worry about that yet. Just write down that H2O plus H2O makes H3O plus OH minus. And this is weird. Okay, this doesn't happen all the time. Again, as I'm talking, you're writing this down here. It only happens like 1 out of every few billion times water encounters water. But there's a lot of atoms of water in a glass of water, or a lot of molecules of water, excuse me. And so, even though it's rare, it matters to us. It actually matters to us a lot. Because remember, we said that acids and bases are defined in terms of this H3O business and the OH minus business, right? And so, if it is true, this reaction seems like we could use it to make acids and bases. That's exactly where they come from. We can just force this reaction to happen more or less by using, well, certain chemicals. Now, on your notes, I want you to remind yourself what the names are. The OH minus is called hydroxide, and H3O plus is called hydronium. You'll hear me use the word hydroxide a lot. You've already heard it a lot this year. But hydronium, this is the first time you've ever heard hydronium. And frankly, it's nice. It's the correct way of doing it. I'm going to use H plus for hydrogen. Why? We'll get there. But hydronium is the proper name, so you should at least have it in your notes once. So again, OH minus is called hydroxide, and H3O plus is called hydronium. And if we add chemicals to this reaction, it will change how they balance. And it turns out, if I add a lot of hydrogen, I get an acid. So, for instance, an acid is defined when, well, the hydronium, or the H+, I don't care which way you put it, is bigger than the OH-. When you have lots of hydrogens and only a little bit of hydroxide, you have an acid. And the opposite is true as well. If you have lots of hydroxide and not a lot of hydrogen, you have a base. And I try to draw that for you already at the bottom of your page, just to kind of remind you that acids and bases are really just coming down to the balance between hydrogen and hydroxide. It's like a tug of war. Whoever's winning, well, that's your acid or your base. If hydrogen or hydronium, whatever you want to call it, is winning, you have an acid. And if hydroxide is winning, you have a base. And if they're perfectly equal, you have water because, well, water is equally likely to split into H3O and OH-. Everything else we do for the whole chapter is about just figuring out how much H+ and OH- we have in our beaker. That's it. Just measuring it, which is really hard to do, but pretty important. That's as close as we're going to get to the math today. So again, we're on this page. Water reacts with water to make H3O and OH-. H3O being called hydronium and OH being called hydroxide. And if the hydroxide is winning, I've got a base. And if the hydronium is winning, I've got an acid. It's easy enough. Well, this is coming about by this guy here, Mr. Reyes. And he gets a lot of credit as a chemist, but it turns out that wasn't really what he studied. For instance, in my field, this person is the first person to come up with the idea that, hey, if we put a lot of carbon in the atmosphere, climate change will happen. And if you look at the dates he's running at, climate change is a relatively recent thing in terms of our narrative, like mid-1980s. This guy was way ahead of his time. And it's not a huge surprise that he was, well, pretty good at chemistry as well. So if you turn your notes over to the next page, we're going to look at what Reyes thought an acid is. And for the most part, like, let's say 90% of the time, his definition's perfect. Okay. An Reyes acid, I'm asking you to define it here, is something which contains hydrogen and makes hydrogen ions. This is the big thing. It has to make hydrogen ions. So again, a Reyes acid contains hydrogen and makes hydrogen ions in water. And a Reyes acid is something that dissolves in water to make hydrogen ions. So over here I've drawn you a little picture of a beaker of nitric acid. What I want you to do is think about if you had like a little ball of nitric acid, something like, let's say this little shower loofah. Okay, this thing is made of HNO3, but the second it hits water, it stops being HNO3 and it becomes H+ and NO3-, right? It splits apart. But think about our definition of an acid. If acids are truly defined by just having more H+, putting something into water that makes H+ makes it more acidy. So Reyes acids pretty much are acids that start with H. It's a really easy way of finding if something's an Reyes acid or not. You're literally just looking, does it start with H? Okay, I think that's pretty easy. But remember, this wasn't something we knew even 100 years ago. Right? Like, the discovery of acids and bases is really quite modern. Okay, so if an acid is defined by H+, then a base is defined by OH-, right? So if I'm defining a Reyes base, which I'm asking you to do here, it's just the opposite thing of an Reyes acid. Something that contains OH and dissolves in water. A soluble hydroxide compound is an Reyes base. Literally, you're just looking for some compound that's soluble. Remember, hydroxides aren't always soluble. That contains an OH ion. And again, if I have some NaOH and I drop in my water, this is no longer just pure Na bound to OH. The Na will go one place, and the OH minus will split out and make the est. So my Reyes acid is something that starts with H, and my Reyes base is something that ends in OH, effectively. I mean, that's oversimplifying things like a little bit, but not really. It's really pretty much that easy. So on this page, there's really only 4 things I'm asking you to write. Arrhenius bases, soluble hydrogen, start with H. Arrhenius bases, soluble hydroxides, end in OH. Easy enough. Of course, actually doing that requires you to know that ions exist. And it turns out once you do know that, and some of the stuff that was being discovered while Arrhenius was studying this, means we can actually come up with a little better definition than Arrhenius did. And that's going to require these 2 scientists. Their names are Bronsted and Lowry. And the 2 of them work together. And I could tell some stories here, but let's just get where we're going. Okay, actually, let's get where we're going by thinking. So on your notes on the next page, I've drawn the boron hydrogen atom. Looks like that, right? You've got a proton, and you've got an electron that just orbits it. Wee, for all eternity, right? Okay, now, if you think about H+, and you only have this, you only have a proton and electron. H+ means the electron went away. H+ is a proton. When you say H+, it is fundamentally the identical thing as saying 1 proton. And these people realize that. They realize that the hydrogen ion is a proton. And they said, we can talk about acids and bases. We know that they do with H and OH. We can talk about them in terms of protons because acids are going to lose and gain electrons. Okay. And so Bronsted-Lowry acid, we're just going to name the acid after their theory, is a proton donor. You literally just need to write the words proton donor. So when I ask you to find a Bronsted-Lowry acid in this box, you just write proton donor. It's something that gives up H+. You can see where this is going if you played along with oxidation reduction. If the acid is the donor, there has to be something accepted. If I have a faucet that's giving water off, there has to be a drain. So if the acid is the donor, then the base is the acceptor. Easy enough. Again, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Okay. We need to do a couple examples together. You are so close to done. We're through all the blabbering. Show you the examples, get you done. Let's take like a minute here to look at a video of another robot. So this is actually the end of the game. There's only about 15 seconds left here. But there's another part to this, which you'll notice are these red and blue platforms. They're like staircases. And the robots actually have to climb up to the top of them. In Rockers, we can do that as well. And actually, so far, only about 5% of our teams can. And so that's what we're hoping will help us actually go towards competing at a world's level of this. So again, we won't know until the end of this weekend whether or not this works. It's our first time we can test it on a field competitively. But we think our design is going to work. It's kind of neat to see that play out. Now, in this case, the red team won, and we'll see where we end up as a result. But as things go, it's kind of cool to see these games play out and kind of repetitious as well. But if this is something that interests you, I'm always willing to talk about it because it's a lot of fun for me. So let's take a look at this example. At first glance, things are a little weird here. I've got something being added to water, but that something isn't an Arrhenius acid, nor is it an Arrhenius base. Look, like Arrhenius acids are easy to identify. Like something like HI, hydroiodic acid. That's clearly an acid, it starts with H. Something like HCl, that's clearly an acid, it starts with H. Something like H2SO4, it starts with H, it's an acid. Something like KOH, that's clearly a base, it ends in OH. Something like, I don't know, SROH2, clearly a base, it ends in OH, right? But this isn't that. It's none of those things. It's something different. And that's where Bronsted-Lowry comes into play. So what we're going to do is we're going to connect the things that look similar. So like this ammonia and this ammonium, they look similar. And this looks more or less like hydroxide, right? And this looks like we're going to do redox. And we're almost going to do redox, but we're not. You see, let's think about what happened to go from NH3 to NH4. Well, I add in an H. But I didn't just add an H. I also added this plus here, right? See, to go from here to here, I had to gain a proton, right? I had to gain both the H and the plus. This is weird. This isn't about electrons, and we're still talking about chemistry. And for the whole year, the proton has been off limits to us, and all of a sudden, that's what's happening. And take a look here. I had one H and one O, and over here, I've got two H's and one O. I lost an H, and not only did I lose an H, I lost a plus too, because I was at 0, and now I'm at -1. Like this lost a proton, right? But that makes sense. The proton went from water and got absorbed by the ammonia. So which is the acid? Which is the base? Well, remember, a Bronsted-Lowry acid is a proton donor. It's the one that gave away the proton. So which thing lost the proton? This lost the proton, right? This water gave up its proton, so this must be the acid, which of course makes the ammonia the base. And this makes sense. We knew that ammonia was a base to start, or at least I hope we do. We know it's a cleaning chemical, and most cleaning chemicals are bases. And here we go, we can explain why it was a base. When I come back, we'll talk about something called a conjugate. We'll talk about why this arrow looks weird. Don't worry about that for now. For now, if you can diagram this out for me on your homework, and I'm asking you to do that 4 times, you're great, right? Your homework just asks you to take these things and label what's losing the proton and what's gaining the proton. And just look, did it get a plus? If it got a plus, it gained a proton. Did it get a minus? It lost a proton. It really comes down to about that. Let's look at one more example here for just a second. All right, so I know we just looked at this example here towards the bottom, and I know I've got one more written here that looks like this, which is the hydrochloric acid plus the baking soda. And you know what? Honestly, for what we're doing, you're never going to see a problem like this. So go ahead and just put an X to that bottom example. It's dumb, and I included it because I'm dumb. It's just too complicated. There's some spectators in there, and we don't need that. It's too confusing. It's unnecessary. But I still think you need another example. So turn over the page, and you'll see the homework that I'm asking you to turn in on Monday. And look at number 12. So again, if we're on the back page here, we've crossed out this bottom example, and we're looking at number 12 on the homework, which is really the identical problem I was going to show you as an example, just written in a way that makes a lot more sense. So let's look at that one, because it makes more sense, and it's better for learning what we're doing. And it's not stupid, unlike the other one. So again, the way I'm telling you to do this is to connect the things that look similar. Hey, these look pretty similar to me. These look pretty similar to me. And again, it doesn't matter how you draw the lines or where you draw the lines. I just want you to think about them. Okay, let's start with this first one. This HCO3 minus went up. It got a plus, right? Because it went from minus to 0. And it got an extra hydrogen, right? This went up. This took in a hydrogen. This took in an H+. It accepted a proton. Oops. And here, I had 2 hydrogens, and I lost it. Remember, a proton is really the same thing as hydrogen for these problems. So if I lost a hydrogen, I lost a proton. Okay, that's pretty easy. If you want to think about it however you want to do it, instead of accepting a proton, you can say this gained, I can't type apparently. This gained a hydrogen. I don't care. However you want to write it, just be clear that this added hydrogen. This lost hydrogen. And whatever gains, whatever accepts, that's a base. and whatever loses is the acid. So because this gained the hydrogen, this chemical here, this hydrogen carbonate, this bicarbonate ion, that's our acid. Make some sense? If it doesn't, we'll play with it on Monday. What we're going to do tomorrow is easier. What we're going to do tomorrow is we're going to learn how to name acids and bases. And it'll be a more traditional video with a whiteboard. And it's a really easy note to finish the week on. I know this is tedious. I know that we just went through, God knows, 30 minutes of me talking. Oh, that's awful for everyone involved. And we're over the hump. Tomorrow we learn how to name the acids. On Monday and Tuesday we learn how to work with them numerically. And then we can be back in the lab. Honestly, what's an acid? It's something that has hydrogen. What's a base? Something that creates hydroxide. Okay, this isn't going to be too bad. If the only thing you leave today is that hydrogen makes acids and hydroxide makes bases, you're doing pretty well. Until then, I hope you have a good day, and I look forward to seeing you again on Monday. Bye.